Good morning, everyone, or good afternoon or good evening, depending on what time it is you're watching this. This is a review video going over all of the review topics covered in Unit 7, which deals with permutations, combinations, and the binomial theorem. The purpose of this is not for me to spend time going through specific questions. All of the review questions that you've been given are questions that if you apply the content I'm going to go over, you should be able to do. So to begin with, in this unit we learned about something called the fundamental counting principle, which I call the Bobby-Bear theorem, and the reason I call it that is the very first example that we used to learn this principle dealt with Bobby-Bear. And I don't know if you recall, but Bobby-Bear had 3 different pairs of pants in his suitcase, and he had 2 different shirts in his suitcase. And the question was, if Bobby-Bear had to wear a pair of pants and a shirt, how many different outfits could he try on? And the answer was 6, and we showed all 6 on the board. You know, I think it was an orange pair of pants and a blue shirt and a green pair of pants and a blue shirt, and we listed them all. But the bottom line is the fundamental counting principle says if you take the number of pairs of pants that Bobby-Bear has, which is 3, and you multiply by the number of shirts which he has, which is 2, you get 6. And that's the fundamental counting principle. If you have a task made up of several stages, and you have to do all of the stages, you have to do A, and you have to do B, and you have to do C, then the number of ways to complete the entire task is the number of ways to do each stage multiplied together. So you take the number of ways to do A, the number of ways to do B, the number of ways to do C, and you multiply them. A useful idea here is that the fundamental counting principle really boils down to the word and means multiply. So Bobby-Bear needed to put on a pair of pants and he needed to put on a shirt. So you take the number of pairs of pants multiplied by the number of shirts. Another important idea when solving problems in this unit, although it's not the fundamental counting principle, is that the word or means add. So for example, if Bobby-Bear went out to dinner and as part of the dinner he was allowed to have a dessert or an appetizer but not both, and there were 8 different desserts on the menu and 6 different appetizers on the menu, then the number of ways he could have a dessert or an appetizer would be 8 plus 6, which would be 14. If Bobby-Bear paid a little bit more, maybe he could have a dessert and an appetizer, in which case the number of different ways he could have a dessert and an appetizer would no longer be 8 plus 4 because he's having both. It's dessert and an appetizer. It would be 8 times 4. I realize that the number of appetizers has changed mysteriously from 6 to 4 in my analogy, but I think you get the idea. If Bobby-Bear could have an appetizer or a dessert, you're going to add those 2 numbers together. And if Bobby-Bear was allowed to get an appetizer and a dessert, you would multiply those 2 numbers together. So in summary here with this little bit of business, and means times, or means plus. Always deal with restrictions first whenever solving any kind of problem that involves the fundamental counting principle. So if you were asked to determine the number of ways to arrange the letters of a particular word, but the first letter must be a vowel, determine the number of ways that the first letter can be a vowel first, then worry about the number of ways the second letter can be chosen and the third letter, and on down the line. I think because when we learn the fundamental counting principle, it's included in textbook section 11.1, which is basically called permutations. People sometimes get confused and think that the fundamental counting principle is only reserved for permutations. It's not. It can be used for some permutations problems and some combinations problems. In fact, Bobby-Bear's pant and shirt problem is not a permutation because the order that he puts those pants and shirt on or the order that he selects those doesn't change the outfit that he wears. Factorial notation, you need to know this algebraic definition of n factorial. N factorial is equal to n times n minus 1 times n minus 2. Continuing down the line, multiplying by 1 less each time until you get to 3 times 2 times 1. N must be a whole number in high school math. A whole number are all of the natural numbers and includes 0. So n can be 0 or 1 or 2 or 3, etc. It must be one of those. It cannot be decimals. It cannot be negative numbers in high school math. 0 factorial is allowed, but it doesn't really fit in with that definition that you're looking at here. So we have a special definition for 0 factorial. 0 factorial is 1. Remember that a permutation is an arrangement of items, so the order matters. Sometimes when you're solving a problem, you might have to figure out whether order matters or not, because if it does, the problem is solved differently than if the order does not matter. Couple of quick examples here. When you line up people for a photo, the order in which they stand makes a difference. The number of ways that some horses can finish a race, well, order matters. The number of ways I can give a Tim Hortons gift card, a Boston Pizza gift card, and an Earl's gift card to 3 people in a group matters. Order is important there, because if you get the Tim Hortons gift card, that's certainly different than if you would have gotten the Earl's gift card. We have this special notation. So let's talk about the gift card situation. Let's say we have 20 people in the class, and I have those 3 gift cards, and I want to find out how many ways I can give those 3 gift cards to 3 people in the group of 20. This would be the same as me saying, how many ways can I arrange 3 people in a line out of a group of 20? This would be the same as me saying, how many ways can first, second, and third place in a race be determined from a group of 20? But it would be written as 20p3. And that means, according to the formula at the bottom of the screen, you can answer that question by taking 20 factorial divided by 20 minus 3 factorial. So you would end up with 20 factorial over 17 factorial. And there are certainly other ways to get that. What you could do instead is say there are 20 ways to hand out the Tim Hortons gift card. There are 19 ways to hand out the Boston Pizza gift card. And there are 18 ways to hand out the third card. So the fundamental counting principle says 20 times 19 times 18 would give you the answer. But we could use that formula at the bottom of the page. However, to solve that problem, you would not use the formula at the bottom of the page. You would probably just enter 20p3 into your calculator. And you should know where to access that NPR function on your calculator. Permutations with repetitions. I wish we called it identical items, but your textbook talks about repetitions. We're talking here about arranging items where some of them are the same. So if I'm arranging n items, normally we would say if I want to put, 8 books on a shelf, we would just be 8 factorial. But if some of those items are identical, we've learned that we need to divide by that factorial. So, for example, this could be arranging the letters from the word tooth. And there are 5 letters in the word tooth, so the number of different unique arrangements of those 5 letters would be 5 factorial, but you would need to divide that by 2 factorial because there are 2 T's. You would also need to divide that by 2 factorial because there are 2 O's. If I wanted to park 5 identical blue cars and 6 identical red cars in a row, well, that would be 11 factorial, except for the fact that 5 of the cars are identical and 6 of the cars are identical. So that would mean it would actually be 11 factorial divided by 5 factorial and also divided by 6 factorial. There's lots of different illustrations. If I had 4 chocolate chip cookies sitting in front of me and 3 coconut cookies, and I wanted to eat all 7 cookies, the number of different ways I could eat them would be 7 factorial, but I would need to divide by 4 factorial and 3 factorial. This is a very useful idea to solve pathways problems. So if we take a look at the number of pathways from A to B, always moving closer to B. So I'm starting in the top left corner and I'm going to the bottom right corner. That must mean I have to make, and you can count the blocks here, I have to make 6 moves to the right, and I have to make 4 moves downward. And I could, make all 6 moves to the right first and then move downward. I could do a couple to the right and then 4 downward and 3 more to the right, and then, I guess, 4 more to the right, rather. The order in which I make these 10 moves will tell me a unique path that gets me from A to B. So the question is really, how many ways can I arrange those letters? How many ways can I arrange R, 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 D, 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 D? Because each unique arrangement would be a unique path. The answer is, if I count those, it's 10 factorial. But then I have to divide by the 6 factorial and the 4 factorial because I have repeated items. And that number, by the way, is 210. 10 factorial over 6 factorial and also over 4 factorial is 210. So there are 210 different pathways from A to B. What if I said you have to go from A to B and you have to pass through C? What you want to do in a case like this is just ignore part of that grid. That part that's just disappeared, I'll show it to you again. There it is. You cannot end up in that region. You have to get closer to C, which means for the first part of your journey, you're confined to that 2x2 grid. And then from C, you're confined to that 4x2 grid. And what you need to do here is you need to go from A to C and from C to B. Now there is a typing mistake on your handout. On your handout, I think it says A to B and B to C. It should say A to C and C to B. Well, how many ways are there to go from A to C? Well, it's going to be 4 factorial. You need to make 2 moves to the right and 2 moves down. So that's a total of 4 moves. But you're arranging, essentially you're arranging the letters R, R, D, D, right, right, down, down. And that means you have 2 R's that are identical, 2 D's that are identical in that list. So you divide by 2 factorial, 2 factorial. For C to B, there are moves that are right, 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 down, down, those 6 moves, but you need to take that 6 factorial and divide by 4 factorial because there's 4 right moves, and divide by 2 factorial because there's 2 down moves. I believe this works out to 90. I think from A to C is 6, and from C to B is 15, and 6 times 15 is 90. So there are 210 ways to go from A to B with no restrictions, but passing through C there are 90. This question, this next question, is maybe the most difficult one. If you're writing an exam and I give you that original grid, let me show you the original grid again. There's the original grid, and I say you have to go from A to B, but not pass through C. Well, it turns out in order to solve that problem, you need to solve this problem first. You need to find out how many ways to go from A to B with no restrictions. You also need to solve this problem, how many ways to go from A to B that pass through C, because the only way you can do this, the only way you can find how many ways are there to travel from A to B not through C is to take the number of ways in total and subtract from that the number of ways that pass through C. So a reminder, this is the total number of ways, and this is 210. We're going to take 210 and subtract the number of ways that we just calculated to the left of the screen, which was 90. And if you work this out, you can try it on your own on your calculator. It's 120. So once again, the only way for you to figure out how many pathways there are that are not through point C is to subtract the number of pathways that are through point C away from the total number of pathways. Combinations? Well, a combination is a selection of items in which the order is not important. So going back to my example of having 20 students, if I had 20 students in the class and I had 3 gift cards that were identical, I just have 3 $20 Tim Hortons gift cards, and I'm going to choose 3 people to give those gift cards to, 1 gift card each. That would not be 20P3, that would be 20C3. That's a combination. So other examples include selecting 5 students to go on a field trip out of a group of people. There's nothing special about the order in which I select them. Those 5 students are going to go with me on the field trip. The cards that I get when I'm playing poker on a Saturday night, the order in which they're dealt to me doesn't change my poker hand. The flavors that I choose for an ice cream sundae, if I'm allowed 3 toppings and I say, well, I want strawberry, chocolate, and caramel, then the order in which they put them on the ice cream sundae doesn't matter. The number of combinations of R items taken out of a group of N items is N choose R, and it can be found using this formula. N choose R is N factorial over N minus R factorial, R factorial. If you put this formula next to the NPR formula, you'll discover that NCR is identical to NPR, but we're dividing by R factorial. NCR can be also written with tall brackets and the 2 numbers stacked with N on the top and R on the bottom. So if you ever see something like this, what that means is you're choosing the bottom number out of the top number. That takes us to the binomial theorem, which is the final topic. The binomial theorem is used to expand x plus y to the n, but the number of terms in that expansion is always 1 more than n. That is sometimes a useful thing to know. The general term of the binomial expansion of that x plus y to the n is tk plus 1 equals n choose k times x to the n minus k times y to the k. Basically, one of the main tasks here is if I give you a binomial raised to an exponent, like 2x plus 5y raised to the 7, you should be able to write out any of those terms using that general term formula, or if you have to, using Pascal's triangle. The problem with Pascal's triangle is if you were trying to expand out something that was raised to the 7, then you need to know that there are 8 terms, and that means you need to look at the 8th row in Pascal's triangle. The problem is now you got to spend time constructing the 8th row of Pascal's triangle. Every term in the expansion has the same x and the same y and the same n. However, each term in the expansion has a different k. T1 uses k equals 0, T2 uses k equals 1, T3 uses k equals 2. And just to round this out, once you identify n, you're going to put n here and here. That's the exponent on the binomial. Once you identify k, which is related to the term number, you're going to put that here and here. Of course, x is going to be whatever the first term of your binomial is, and y is going to be whatever your second term is. So it's really just a matter of lining up or fitting in the different pieces in the question, x plus y to the n, putting them into the general term. And we've done lots of examples over the past couple of lessons dealing with that. I hope that that video is a little bit useful for you. Again, you need to now get down to work and do as many permutations, combinations, and binomial theorem problems as you can, because when you talk about the fundamental counting principle with permutations or the fundamental counting principle with combinations, there are just boatloads of different examples. And we've gone through as many as I think will get you ready for the exam in class as possible. but doing more and more in the review problem set is certainly going to improve your odds of doing better on the exam as well. So enjoy your Christmas break. Have a very wonderful Merry Christmas, and we will see everybody in the new year. Take care.